So, welcome to the second lecture on implementation of simple linear regression using R. In the last lecture, we saw how to read a data from a text file, how to visualize the data, how to build a linear model and how to interpret it. In this lecture, we are going to look at simple linear regression model assessment. As a part of this, we are also going to look at how to identify significant coefficients in the linear model. Now, let us start with model assessment. So, there are a few questions which we need to answer before we go into model assessment. After having built a model, we first need to check how good is our linear model. Now, we need to identify which coefficients in the linear model are significant. Now, if you have multiple independent variables, then we also need to identify which of them are important. We also need to know, can we improvise the model further? As a part of this, we are going to look at, are there any bad measurements in the data? So, by bad measurements, we mean, are there any outliers in the data which could affect the model? This question alone will be handled in the next lecture. So, let us look at how to answer the first two questions. Now, from the earlier lecture, we saw how to look at the summary. We also know how to interpret it now. Now, this is the first gist of summary that you get when you run the command. So, I had regressed bit price with coupon rate from the data bonds, and bonds mod was my linear model. I also have the estimates here, which are nothing but the intercept and slope. So, let us look at the first level of model assessment. So, the first level of model assessment is done using the R-squared value. Now, if you go back and see, the R-squared value for our model is 0.7516. Now, this is pretty close to 1, though not very close, but it is still closer to 1. So, we can say that yes, the model we have developed is reasonably good, but not really good. It also tells us the assumption that we made initially to begin with, that there is a linear relationship between x and y. We are also going to look at hypothesis testing. As a part of this, we are going to look at the hypothesis testing on coefficients and then on the full and reduced model. Now, let us see what these full and reduced models are. So, first let us do the hypothesis test on coefficients. So, in order to check if your linear model is good, we can check if the estimate beta 1 hat, which is the slope, whether it is significant. So, my null hypothesis is beta 1 hat, which is the slope, equal to 0. So, this means that yi hat, which is my predicted value, is equal to beta naught hat, which is the intercept, plus epsilon I. We also learned in the earlier lecture that this epsilon I is the residual. Now, this becomes my reduced model since my slope is equal to 0. So, what will the alternate hypothesis be in this case? So, my alternate hypothesis is that beta 1 hat not equal to 0 and my yi hat, which is the predicted value, is equal to beta naught hat plus beta 1 hat xy plus epsilon I. Now, this becomes my full model. The confidence interval is computed to check if the slope is significant. Now, this test is a two-sided test, since we see if beta 1 hat is equal to 0 or not equal to 0. At 95% confidence level, that is at alpha equal to 5%, we get the critical value to be 2.0345. Now, let us see how to compute this critical value. So, we know that alpha is equal to 0.05 and n here is the number of observations in your data. Now, in this case I have 35 observations. P becomes my number of independent variables. Here I have only one independent variable. So, now we know from the statistics module how to compute the quantiles for a t from a t distribution. Now, I give p equal to 1 minus alpha by 2, since it is a two-sided test, and the number of degrees of freedom are given as n minus p minus 1. So, this command is inbuilt in R, you just need to give the inputs. So, you need to supply p and degrees of freedom. After having done this, we get the quantiles to be equal to 2.03. So, this is the critical value. We are going to use this to compute the confidence interval. Now, we earlier saw from the summary that the slope, which is nothing but the beta 1 hat, is equal to 3.0661 and the standard deviation associated with it was 0.3068. So, the confidence interval is computed as the estimate plus or minus the critical value into the standard error. So, by doing so we get the lower bound as 2.44 and the upper bound as 3.69. So, now we know that this interval does not encompass 0, that is anywhere between the interval I do not have 0. So, this itself is indicative of the fact that my beta 1 hat, that is the slope, is significant. Now, let us do a hypothesis test on the models. So, to do so we use the F statistic. So, let us go back and revisit what the F statistic is. So, F statistic is nothing but my sum squared residual divided by the sum square error by the degrees of freedom for the denominator. So, for the sum squared residual, we know it is of the form of summation of yi hat minus y bar the whole square. So, I have only 1 degrees of freedom since I am using only one parameter to compute it. Whereas, for the sum squared error, it is the summation of yi minus yi hat whole square. Now, I am using 2 parameters to compute it. So, the degrees of freedom reduced by 2. So, hence I have the denominator as n minus 2. So, this is how you would compute the sum squared error. So, I am summing my yi, which is nothing but from bit price bonds dollar bit price. I have the fitted values and I know the mean, which is y bar of the bit price. I am squaring the term and I am summing it. Now, we know that the number of observations we have are 35 from the data. So, from the formulae we know our F statistic is computed as SSR by SSE into n minus 2. Degrees of freedom n minus 2 go to the numerator and we get the F statistic to be equal to 99.87. Now, this F statistic is what is returned by the summary, which is given in the last line of the summary. So, let us see what conclusions can we draw from these two tests. We know that the F statistic from the table 1 and 3 degrees of freedom is 4.17 at 5% significance level. What we observe is 99.87 at 1 and 33 degrees of freedom. Now, this is greater than the theoretical value that we get from the distribution. So, what conclusion can we draw now? So, we know that we can reject the null hypothesis since the confidence interval does not include 0 and hence beta 1 hat, which is the slope, is also significant. So, in this lecture we saw how to assess the model. We also looked at how to answer some of the important questions that gets associated while assessing a model. We also saw how to identify the significant coefficients. In the next lecture, we will look at how to identify outliers and how to improvise a model. Thank you.